AMD's launching some new chips. Can I interest you in some SP5? So recently AMD invited me to Austin AMD HQ, where I could take a look at their new SP5 test platform, codename Titanite. Now, the Titanite platform is AMD's test platform. It's literally their test platform. And they were kind enough to ship one here to the office so that I could take a deeper look. Exciting times, let me tell you. The box was enormous, and yeah, there's some marketing stuff in it, but I unpacked it and I got it deployed in a rack here. It's configured for 220 volts, 2,000 watt power supplies, SP5. Configured this system with 1.5 terabytes of memory, up to about 14 NVMe drives, well, like 28 if you count the M.2 that are in the back as well, because, oh boy, it's got a lot of PCIe lanes. And I ran it through a full suite of benchmark tests. 96 cores, 1.5 terabytes, and all sorts of new information. And we'll get to that, don't worry. I've actually got a full rundown of performance and all the new features and everything that's here, but before we get to the performance and the benchmarks, this is a new platform. It's DDR5. It's registered error correcting DDR5, which we haven't really seen before. It turns out it's all going into this. It's a new socket, 12 memory channels. It's a totally new platform. There's a lot to talk about here. And not only was AMD at AMD's event, but also Microsoft, TigerGraph, Ansys, a whole host of enterprise companies, some of the largest companies on earth in terms of compute and compute customers, that have all had early access to this platform, and they've done their own testing, and they shared numbers with us and also test scripts and everything else. So we've really gotten to take a deep look at this platform. Let's dive in. There is so much I want to talk about. I'm just going to have to do this across several different videos because this is a huge launch. Make no mistake. I think this is probably the most important platform that AMD's ever launched. Well, okay, it's probably about as important as the Zen launch, but in the grand scheme of things, it may actually be even more important than the Zen launch. AMD is telegraphing what they are going to be doing for the next 5 or 6 years with this launch. It's a new platform, SP5, DDR5, and their whole enterprise compute strategy. It's not just the upgrade for new generations, PCIe 5, this sort of thing. It also sort of signals that AMD is maybe going to lead because they're listening to customers and they're going in sort of their own direction, or they're going in a different direction. I mean, don't get me wrong, the benchmarks are impressive. And, you know, in their own slide, they say it's a 14% IPC uplift. And that by itself is pretty good, but it's not the best that we've seen from AMD. But don't think that this is just about IPC. We also got a huge bump in compute per watt efficiency and the frequency. So the frequency's gone up, the power usage has gone down, and we're still 14% better IPC. So 2x, 3x, 4x improvements in the benchmarks? Yeah, when you're actually talking real world work. AVX 512, they've added that, but it's not just about AVX 512, there's a strategy component to that as well. AMD's using AVX 512 to accelerate specific workloads, and that's their answer to doing silicon stuff that's going to take up more real estate for workload-specific acceleration that only works in that specific situation. I mean, this thing's got 700 gigabytes of memory bandwidth now with DDR5, plus supports for terabytes beyond that when you leverage CXL, so 6 terabytes per socket plus terabytes beyond that. And in-memory things for neural networks, like what TigerGraph, the company, is doing, it's sort of transformational for those workloads. Now, PCIe 5, for shuttling data in and out, that sort of ties everything together. So this platform, it really is doing a lot. And a good chunk of the 400 watt socket power budget isn't even going to the 14% IPC uplift in compute resources. It's the memory interface, it's the PCIe 5 system, it's all of the other stuff. So when you think about it that way, and what AMD has done on the compute side, 96 cores on the order of just 1 watt per core, just for the compute aspect of it, this might be the most important platform launch in a decade. Maybe even more important than the original Zen launch, Zen 4. It's pretty big. So in addition to the 96 core CPUs, I also have the 9374F CPUs. These are frequency optimized. That means they're fast, really fast per core. 4.3 gigahertz CPUs that are 32 cores, as well as our 9554, which is a 64 core variant of our new SP5 CPU. And this makes it pretty easy to compare to other 64 core CPUs like Milan and Milan X, the CPUs that I have on hand. Let's talk changes to the naming convention. The EPYC 9000. Is it really over 9,000? Well, yeah, I mean, I think so, obviously. But the numbers give us some different clues. First, they moved the letter to the end. So P for the cost down single socket versions of CPUs. You should always get a P if you're going to get a server chassis that only has one socket. I mean, you're just saving money. It's a no-brainer. F for the frequency optimized parts, the letter moves to the end. The last number stays the same generation, so in our case we're going to look for number 4 everywhere. And then the two middle numbers give us some other clues. The first middle number is how many cores it has, and the second middle number is the relative performance for the number of cores. So for a 9554P, the 5 indicates that we have 64 cores. Could be 6 for 84 to 96 cores, all the way down to 0 for 8 cores, or 1 for 16. So depending on where it is in the product stack, can have a 9054 or a 9154 or a 9554. Then the performance is the tens digit. So our F CPUs, of course, they have a 7 there because they're also F and really fast. But sometimes it's not always as clear cut because you don't necessarily have the F. You may need something else to give you a clue that the relative performance here is high, because there's multiple 64 core parts, for example. One of them is a little faster than the other. And oh boy, those performance numbers. Woo! Now for our test and comparison systems, this is AMD's Daytona platform. This is the platform that got the Cinebench world record, and this is the platform that AMD brought up both Rome and Milan. Currently it has my 64 core Milan CPUs in it. If you've ever come to the Level 1 forums for help with your open source project and I let you remote into a system, chances are it was this system. I don't have the memory fully populated and some other stuff configured, but this is what we're using for our comparisons with Genoa. It's configured for NVMe at the front, plus SATA, plus I've got plenty of PCIe connectivity. The Daytona platform was great to learn on, really putting AMD's EPYC processors through the test. But it did struggle a little bit with the 280 watt Milan processors. Enter the Gigabyte platform. So this is our Gigabyte platform that's running two Milan X 64 core CPUs. This is the other system that if you've remoted in, you probably were using this system if I was helping you with an open source project or you needed access to an EPYC system in order to do testing. ZFS, when I was building Greg Crow-Hartman's machine, this is what I was using. This motherboard from Gigabyte was the first motherboard available to really let the 280 watt Milan X CPUs sing. And so this is what we're using for our comparison. Actually, this system has been running the Red Hat OpenShift platform for the better part of a year whenever I didn't have something else for it to be doing, so that we can test clusterization, container management, so on and so forth. The reality is that Milan X, two 64 core processors plus all that cache is so powerful that you can run like 3 Red Hat OpenShift clusters on this. And so Greg at Red Hat is the one that helped me set all this up and get everything going with OpenShift. And this is what we're using for a comparison OpenShift platform. I mean, this one system could outperform some of their old Xeon V2, V3 clusters, the entire cluster, just one machine. So I took that and I ran with it in order to test the Genoa platform with OpenShift. And so that's what we're running. Now for a lot of our benchmarks, we're using the Phoronix Test Suite. And you can check out the full results of our benchmarking at openbenchmarking.org via the Phoronix Test Suite. So yay! Open benchmarking! We've also got, on comparison, a Xeon 8380 system. That's a dual platinum 40-core system, and those CPUs are running unlocked with the unlocked PL2 power limits. So yeah, those CPUs can be pretty fast, especially with AVX 512. Now, I think there is some limited coverage of Sapphire Rapids that is going to be available, Intel's next generation CPU, but those aren't launching until January 10th. We've got a ways to wait before we see the real skinny on Sapphire Rapids, I think. One of the most surprising things in a lot of the benchmark results is just how well 96 cores scales. That's sort of nuts. I mean, we hit a wall compiling the Linux kernel because the Linux kernel wasn't big enough. LLVM quite a bit bigger. And now we can compile both of them in roughly the same amount of time, which is nothing down to CPU. It's really just the overhead of everything else. This platform really goes kind of a way to eliminate some of that overhead because faster memory, faster I/O, lower latencies. I also used the core-to-core latency tool to generate a graph of what we're looking at when we're going cross-chip, cross-CCD with some different latencies. I found it pretty interesting for the 96-core part, and the 32-core part was about what I expected. So no surprises there. At the AMD event that they had in Austin, there were a couple of representatives from companies that do 3D rendering and compute rendering and that sort of thing for Hollywood movies. And they had early access to Genoa-based systems as well. And they were very, very complimentary. That sort of follows through with the Phoronix benchmarks and the sort of, pleb tier rendering that we're doing here. Yeah, Genoa's real fast. AVX 512, the Blender benchmarks, a lot of the Blender benchmarks are completing so quickly that between the 32 and the 96 core parts, there's really not a lot of difference because what used to take minutes to render is now 20 or 30 seconds. We got to use much larger Blender benchmarks in order to tell the performance story here because 96 cores rocking a pretty high clock speed for what it is a significant render engine for this kind of work. For the Disney materials scene, for example, in Appleseed, our 9374F, which is only 32 cores, could outperform our dual 64-core third-generation EPYC monster. There's that much of a gen-on-gen performance improvement for some of these types of workloads. And remember, when looking at benchmarks like the PyBench and the PHP benchmark, yeah, these CPUs are monstrous. It looks like the 9374F 32 core is outperforming the 96 core, but what you have to keep in mind is that these benchmarks are single-threaded. So a single thread on our dual 32 core machine is performing very nearly 1 million operations per second in PHP, but we've only got 64 cores as opposed to 192 cores where each core is 2/3 as fast. When you're running a PHP web server, the 96 cores thing will scale pretty well. And it's kind of the same story with Python. I mean, from 64 cores on 3rd generation EPYC to 96 cores on 4th generation EPYC, pretty respectable improvement from 900-ish milliseconds to 800 and some milliseconds. To the 32 cores, 762 milliseconds. And these are really, really good numbers, depending on if you want to maximize the number of cores in a box, or you want to maximize the performance of a single thread or two that's running on this platform, just depending on what your use case calls for. We switched to Windows Server in order to be able to do some of the Windows benchmarking, and the Windows version of Geekbench really shows that for these servers, I mean, this is getting close to Zen 4 desktop levels of performance, but in a server form factor, especially when we're talking about the 9374 CPU. I mean, the F isn't just whistling Dixie. It really is a frequency-optimized part. This giant red bar, yeah, that's the 96-core monster 2-socket, and it just sort of dominates everything else because it's got 96 cores. Yeah, I'm just reviewing the results from the benchmarking, and you should know that AMD actually has a lot of application notes which have valuable information in them. All of these PDFs are specific applications, things like Nginx or Apache Cassandra or JVM or MS SQL Server, Kubernetes, whatever it is that you're running. And a lot of these application notes feature things like the NUMA topology diagram. You know, we have 12 memory channels and 4 groups of 3 chiplets, 12 chiplets total for up to 96 cores if that's what you have. And there's a lot of valuable information in there because sometimes you don't get 367 million nodes per second in ASM fish right out of the box. Sometimes you need to do a little bit of tuning depending on what your workload is. And sometimes even just tuning for Microsoft SQL Server varies depending on what workload you're specifically running in Microsoft SQL Server. So I'm sure that the numbers that I have are not the absolute best numbers that you can get. It may be possible to tune specific workloads, but there wasn't really that much time between hands-on and launch time, so I sort of had to rush things a little bit with this testing. But know that the application notes exist, and you can get those from AMD's website. I'll try to link a few of them below, or at least link you to where you can go to get them, because they are hugely valuable resources for tuning one of these systems if you decide to pick them up. Take, for example, Apache Cassandra optimization. Disabling transparent huge pages. Linux distributions enable transparent huge pages by default, which makes the kernel try to allocate memory in large chunks, usually around 2 megabytes instead of 4K. That's hugely experiential knowledge shared with you in this PDF. It's there for you, for the reading. And there's so many other valuable nuggets like that if you're setting up a system. For me, a lot of this kind of stuff is second nature, but it's nice to see it documented for these platforms. It is great. That is part of the ecosystem that AMD needs moving forward, and this is one of the reasons why they're sort of capturing so much market share in the data center space, is because, hey, we wanted to make it as easy and as paint by numbers as possible. They're listening to customers. That's what customers want, and that is a big part of it. Just, okay, give us the paint by numbers of how we make Cassandra go fast. Thanks, AMD. Another way that I know that AMD is listening to their customers, their data center and enterprise customers, which benefits all of us, even people buying servers at the pleb tier, that is the open BMC interface that AMD has built, they call Hawaii. So there was a bit of a kerfuffle last year because an article came out in a major publication that said, oh my gosh, this grain of rice-sized chip is in your computer and people can take it over. That was never really substantiated, but it is a theoretical attack that's possible. And because of all of the press that got, a lot of people started thinking about how do we make the system more secure. And this is kind of the result of that line of thinking. You see, having your server and your server operating system and everything being perfectly secure, you still need a way to manage the server. How do you remotely install an operating system? How do you remotely inspect sensors? How do you remotely deal with this, that, and the other? And if you're no stranger to this channel, you know that when we cover servers and server motherboards and workstation motherboards, we talk about that remote management component. Usually it's built around a controller like the ASpeed 2500, 2600, something like that gives you a remote monitor capability and a remote sensors capability. And these are usually plugged in pretty deep to the system. They can access the system management bus. They can typically access certain parts of the real physical hardware of the system. And what makes it different, is that not only did AMD design their own add-in board for this, but now there is a standard for sort of decoupling that from your motherboard and your platform. You can build your own custom thing. But it also has the TPM module interface, so it's got all the cryptographic plumbing if you really want to lock it down. So you can go all the way from designing your own baseband management controller or your own management platform, as I'm sure Microsoft and Amazon and other companies like that are doing, all the way down to, if you're a smaller company, you can just validate the firmware images cryptographically and sort of deal with the management controller out of band as well. So the Hawaii module from AMD incorporates a 2230 M.2 micro SD card slot, a micro USB interface, a mini DisplayPort. Don't worry, there's VGA at the front. Good old VGA is not going anywhere, at least not for a couple more generations. But we see DisplayPort, mini DisplayPort. So there is a digital interface. There's hope that maybe someday VGA can go away. The 1 gigabit management interface, and all of the other cool stuff on this module that you would expect for remote management. But it's really awesome to see that it's modular, because that module can be protected a lot better from supply chain hacks and any other nefarious thing that somebody might want to be doing with this at different points along the supply chain. So it's really cool to see this in this platform. So let's talk AVX 512. It's launch day, there's going to be a lot of coverage about AVX 512, and it's Zen 4, so maybe it's not really much of a surprise. Hey, AVX 512 is a thing on these new EPYC 4th generation CPUs. But what you might not realize, what I didn't realize, is how much of a strategic decision that also was from AMD. I met Michael Goyne from Neural Magic. They've got Deep Sparse and something they call Sparse Zoo, and they're doing AI on CPUs. AI on CPUs? Really? Why would we be doing AI on CPUs? So one of the things that you'll see in the benchmarks is things like absurdly fast ResNet 50 AI inferencing workloads. And it's not just because the CPU is fast. One of the things that everybody is trying to attack with that is, oh, let's switch to int 8. Let's do int 8 with VNNI and do fun stuff with AI in order to make AI go faster. These are really software optimizations. And these are available across all platforms, assuming that you have the instructions integrated. And that's what AMD has done. But it's a larger strategic decision than I had really realized. You see, with competing CPUs, they're dedicating a lot of silicon real estate to other types of accelerators that can help with AI-type workloads. Instead of doing that, AMD is providing AVX 512, which will provide accelerated vectorized instructions, which helps across a whole host of things. AI, sure, yes, but also we'll learn about what it's doing for Hollywood and everybody else. But you dovetail that with a sparse matrix approach, as Neural Magic does, and then you get something really special.
Hi, my name is Michael. I'm with Neural Magic, and we focus on sparsifying neural networks to great amounts while maintaining the accuracy of those models. And through this unique architecture, we're able to fit these large models and compress them onto CPU devices, getting them to GPU level speeds. And we're really excited about the early access we got to these Genoa systems from AMD and the performance we unlocked from Milan to Genoa. So CPUs make a really compelling use case for AI inference because they're ubiquitous. They're commodity hardware, and really the unique architecture of them, of having large amounts of cache for each core, allow us to store these compressed models in the resident cache of each of these cores and really accelerate the performance by an order of magnitude, getting CPUs to the GPU class of AI inference performance. So, and in a really common use case that we see in our customer engagements of retail object detection, we were able to get 18 cameras running at 30 frames per second each on a Milan-based system. And moving to Genoa, we were able to get up to 64 cameras at 30 FPS. And for many of our engagements, we've heard that 3 to 5 FPS is more the target of frame rate that they're looking for. And the question is, how many streams can we get with that? And so we were able to get over 300 streams of video running at 5 FPS each on the latest Genoa hardware. And so we're really excited to take that with our partners and engagements.
I also met Serena Sit from AMD, who wanted to talk a little bit more about ZenDNN.
My name is Serena. I'm a part of the AMD Server Business Unit, managing AI for AMD EPYC. Now, AI has been top of mind for many of the top companies in the industry today, and AMD is no exception. And so one of the things that we're focusing on in the AI space today is actually to really improve the customer experience and the developer experience, because AMD has such a wide portfolio of hardware products. We've got AMD CPUs, GPUs, FPGAs, adaptive SoCs, and we want to make sure that customers get the best out of the heterogeneous systems that they're developing using these AMD products. And so for AMD EPYC in particular, we have a library called ZenDNN. It is our AI inference library that optimizes inference execution on EPYC processors. And it operates at the level of providing optimized primitives, such as AMD-tuned implementations of convolutions, ReLUs, functions of that sort, as well as providing graph and framework optimizations so that customers can really unlock the best of AMD EPYC for the machine learning deployments.
And ZenDNN is not quite ready yet. We're probably going to see that around the beginning of 2023, but the deep learning network here is going to make this a little bit more accessible in an API format for programmers pretty much across the board. Now, what Neural Magic is doing here with their platform and the things that are going into ZenDNN to make it available for everybody, not just for sparse networks. I mean, that's kind of their speciality, is all of these neural networks that have been converted into sparse networks so that they'll run insanely way faster. I mean, we're talking about a difference of 83 images per second on Zen 3 to like 1,600 images per second with ResNet 50 with the sparsified matrix and int8 VNNI instructions. Just a lot of the hardware acceleration that we see in Genoa. So AMD's really shining here with AVX 512 in the server. And it also runs at basically full clock speed. This is one of the few workloads where I was able to actually really get the CPU to consume the full 400 watts through the socket, but it didn't downclock. In fact, it was going higher than the base clock as long as I could keep the thermals under control at 400 watts. So there's no clock speed shenanigans or anything like that. It's just running at full speed, basically. Well, now, the implementation under the hood, it does take a couple of cycles to get through most AVX 512 instructions. You're going to do everything 256 bits at a time. That's actually something really clever that AMD has done with their implementation, but the CPU doesn't have to slow its clock speed in order to do it. Another new feature of this platform, CXL, Compute Express Link. CXL is something that's been in development forever, but hasn't really been taken up a lot by the server industry. It is The easiest way I could describe it is it gives you a way to attach memory type devices over the PCIe bus. And we were talking PCI Express 5, it doesn't have to be PCI Express 5, but it's useful because you could have a cluster of servers connected to a shared bank of memory, and then if one of the machines in the cluster drops out, you're able to read whatever was in the shared memory without having to go into the memory that's inaccessible because the thing's actually offline. It's more interesting than that. There's actually a lot of uses, a lot of interesting uses for CXL. And without going too far off track here, the best use that I've seen so far, and something that's going to be widely available with CXL, is with a limited amount of persistent memory to really, really accelerate database-based workloads. You see, when you're building a database, if you want the database to be able to survive a catastrophic crash or other sort of bad situation, you need to maintain the state of what the database was doing in memory. One of the solutions was to use entirely persistent memory for the complete whole other system. So when the system is crashed or something bad happens and it reboots, it can just resume where it left off because everything that was stored in memory is available. As a practical matter, that doesn't really work. And it wasn't necessary, it turns out. In order to build a monster honkin' database system that will scale with 96 cores and beyond, you really don't need all of the memory to be persistent. You just need the stuff in the memory around the transaction log to be persistent, and bonus points if it's accessible to other machines. Something faster than an Ethernet interface, something faster and more reliable than just a raw PCIe interface, something like a CXL device could do that. And so AMD provides full support for CXL 1.1 with limited support for other stuff in the CXL standard to enable that kind of functionality. This protocol is what's called cache coherent, which means that as stuff is happening with the data manipulation, the cache inside the CPUs, the cache memory, the things that actually make computing not horribly slow, are sort of aware of the things happening outside the CPU and vice versa. So you can complete transactions, you can complete operations in a way that is coherent with the cache in the CPU. As a practical matter, if you're just in Linux and you list the contents of the system, you'll see a NUMA node that doesn't actually have any compute resources, but just has memory resources in one of the ways that it's attached. And in fact, the Linux kernel just got some patches to support about 6 tiers of memory, because this is kind of where the industry is headed, is multiple tiers of memory so that you don't necessarily have to do I/O operations in order to be able to do this, because doing an I/O operation is too much overhead. It needs to work more like memory and less like I/O. Now, the reality is that the industry is probably not as far along with CXL as everybody expected, but to see this level of support for CXL in the SP5 EPYC 4th generation platform, actually really pretty exciting. This may pave the way for some really innovative devices to come down the pike and share PCIe devices and memory devices and that sort of thing with other systems inside a cluster, or whole new levels of resiliency. This feature is going to pave the way for all new levels of computer science and research, which that on its own is pretty exciting. The other thing this can enable is systems to support truly absurd amounts of memory. Now, as I've said, you can do 6 terabytes of memory on the 2-socket platform, with SP5. 6 terabytes, that's cool. But you can do many, many, many times beyond that with a full CXL system. Of course, I'm not aware of any of those systems that actually really truly exist at this point in the retail space, but there are test fixtures and lab machines and things like that that offer tens of terabytes of memory available through a CXL attachment. And the latency really isn't completely terrible because we're working with PCIe 5 levels of bandwidth. So, Another important thing about CXL is that it works with the encrypted memory subsystem that's part of the EPYC architecture. So 6 terabytes per socket, yeah, okay. But you can go terabytes and terabytes and terabytes beyond that, and it supports over 1,000 keys, and that's huge for enterprise customers because the host machine could have that high-speed CXL interface to somewhere else. It looks like a PCIe interface, really. And that is doing stuff with memory, but then that device can read stuff from memory. That's not really secure, right? Well, no. The CPU has its own encryption controller, and so the off-chassis stuff is encrypted. Let's talk chiplets and I/O and memory. All right, first up, DDR5 4800. That's fully supported. most configurations are going to be 1 DIMM per channel, and it's 12 memory channels, so this is an unprecedented amount of memory bandwidth. And there's also something that's sort of curious. Depending on the Linux kernel version and some system tuning parameters, I'm actually able to get close to the full amount of DDR5 bandwidth. If you remember on Zen 4 on the desktop, we were seeing about 75, 78 gigabytes per second, give or take. That leaves us a little bit of memory headroom. Where's it going? What's the interface? Well, on the server platform, we don't seem to have as much headroom. Well, it's maybe not the way that I should say that. The chiplets seem to be able to talk directly to our registered error-correcting DDR5 memory at full speed. There's no limitation. There's no anything to worry about. Is this updated microcode, difference in platform? I don't know. But the I/O die here is pretty big. They had some delidded chips that we could see at the AMD presentation, and yeah, 12 chiplets plus the I/O die, 3, 6, 9, 12 in 4 quadrants. Now these CPUs do support, the NPS 1 through NPS 4 non-unified memory domain configuration. So if you have a really latency sensitive application, you can run these CPUs with multiple NUMA domains, and it'll try to group the chiplets sort of close together with the memory that's physically there and all that. None of that is really new, but it does support running, 12 memory channels, 10 memory channels, 8, 6, 4, 2, and 1. But really, AMD recommends that you run with as many memory channels as possible to get as much bandwidth as possible. One big change this time around is that if you're going to run 4 chiplets, you actually have dual GMI links. They call it GMI wide. GMI is the interface between the chiplet and the I/O die. So this is something that we saw on some of the less expensive P-series EPYC SKUs. So you could have fewer chiplets with those as well. You could get to 32 cores with, some 4-core chiplets or some 8-core chiplets, 4 8-core chiplets or 8 4-core chiplets. So both of those add up to 32. And in fact, AMD had both of those SKUs, one more expensive and one less expensive, depending on what your goals were and what you're trying to do. You also get more cache and the benefit from having more chiplets, yada, yada, yada. But sometimes all you really need is a lot of memory capacity or a lot of I/O bandwidth, PCIe lanes. And if you're going to use a lot of memory bandwidth and a lot of PCIe lanes, then it would be nice to have fewer chiplets that could keep up with that. And that's exactly what you get with the wide GMI link. So this is pretty genius. So with our interface chiplet, our I/O die, 128 PCIe lanes, that's basically the same as before, except now PCIe 5. Now it's up to the system integrator to decide they want all the lanes to be PCIe 5 or 4. There's actually more than 128 PCIe lanes because there are some quality of life PCIe interfaces to make it easier for system integrators. And of course, those PCIe ports can be configured a number of different ways. It's 16 lanes. Some of the ports are CXL compatible, so you can have CXL devices in a PCIe configuration, but you still have that coherent memory protocol access and all the stuff that goes with that. But you can also configure a 16-lane port as an X8 device and 8x1 devices, up to 9 devices per port. So yeah, you could have 8 PCI Express by 1 lanes plus 1 X8 device on 1 X16 port on your AMD EPYC CPU, and you can do that for pretty much all the ports. This gives system designers a lot of flexibility. In fact, as we saw in our Titanite test platform, there are CPU PCIe bridge cables. If you want to configure 64 lanes between each CPU, or if you want to have fewer links between your CPUs, you can configure that by just physically removing cables and then using those cables, which give you more PCIe lanes, 16 lanes worth, to go to peripherals if that's what you want to do. But if you're doing system architecture or building a system or something like that, that's really cool. That's not, removable cables like that is not really a feature that you would see in a, totally retail system, I think, but this is just for debugging the platform and doing other sorts of interesting tests like, hey, does it really bottleneck us if we don't have 64 lanes between our 2 CPUs to do inter-CPU communication? I mean, it is PCIe 5 after all, right? Should be fine. All that PCIe 5 and DDR5, don't forget that the Infinity Fabric is also running at these ridiculous, insane speeds. So it really is infinity. I get what they mean by Infinity Fabric. It's just going to keep scaling to infinity, it seems like. I mean, all of the crazy stuff that I was doing before with NVMe and memory and I/O, all of that's gone. Like, the thing is so fast that now the Zen 4 cores are the slowest part of the equation. And those are insanely darn fast. And even as insanely darn fast as they are, we have more memory bandwidth and more I/O bandwidth than we've ever had. So yeah, when I say that this platform has aspirations for the future, that's what I mean. You really do see a lot of hints on the Zen 4 platform and SP5 that signals that AMD is going to open up a whole bunch of what they call swim lanes for new products. There's a lot of groundwork here. As amazing as Zen 4 is with all of the stuff that it's doing in 4th generation EPYC, you can tell that AMD has some even bigger plans for this and that are going to slot right into this platform. It's pretty exciting, but also a little bit scary because of how monstrous this platform really is. Now, I do almost all of my testing on Linux, but it's nice to know how the other half lives with Windows Server. AMD fortunately brought in Jeff Woolsey. He's from Microsoft. He works on Azure stuff. And he was really complimentary of this new platform. He's finding a lot of the same things that I was finding in terms of the interface speed and how well everything runs and how balanced the platform is. Not just the cores, but also how you feed the cores with I/O and storage and everything else. He talked mainly about the SQL Server team, so that sort of gave me an idea. I'm going to reach out to Glenn Berry, and we're going to do some SQL Server tests. Now, you're probably not going to get a 96-core system for SQL Server because the licensing would be on the order of $1 million if that's what you're actually going to, run with. But the more modest F-series systems, okay, yeah, maybe. 32 cores, 24 cores, 16 cores, the per-core licensing, it's a pretty good deal. And Microsoft is paying a lot more attention to these kinds of things with their scheduler and performance improvements and the system architecture in general. That's what 5 years of wins looks like, because people are taking AMD seriously. But yeah, we knew SQL Server performance was going to be breathtaking. We've got 96 cores that we're packing in here, but what about everything else? Well, there's Azure Hyper-Converged Infrastructure. He said that they've been testing a 2-node cluster. They're one of the few solutions that actually supports a 2-node cluster. But you can deploy Azure HCI, and your on-premise cluster becomes basically an availability zone. I'm not using the right Azure terminology here, and I'm grossly oversimplifying, but you can deploy that, and you can have a 2-node cluster on-premise that integrates pretty cleanly with your stuff that's in Azure. And this platform is basically already certified to do it. They've already got previous gen EPYC solutions that are available for that. And Azure HCI is something really exciting because this is a fire-breathing amount of horsepower that you have on premise. And because of that, you're going to be able to run insane workloads locally, but you can also have the data assurance and integrity and everything else that you do from Azure policies. So he talked about how you basically could be in a situation, if you wanted to be, where Microsoft is doing administration of Kubernetes and containers and even old legacy Windows containers. Like, they don't even charge you for Windows Server 2008 support if you're doing it on this Azure HCI infrastructure that they support directly. Because you can take whatever legacy application it is, put it inside this weird container that's old Windows, but it's not really quite the same as running old, not supported, we charge you a service contract Windows type instances. And of course, with 96 cores per socket, you imagine you can get a lot of work done from 2 servers that have 2 96 core CPUs each in your local cluster. And yeah, Microsoft was really pretty excited about it. My other big takeaway from chatting with Jeff Woolsey from Microsoft was that the AMD Microsoft partnership goes back a ways, and AMD is listening to its customers to build these things. Microsoft says, gosh, it would be nice if we had, and then AMD says, yes, we will build that into the next generation. So some of the things that I bumped up against with Milan and Milan X in terms of performance and some of the crazy stuff I was doing with IOMMU and everything else, I mean, the enterprise is kind of doing something similar. Microsoft was doing something similar, albeit at a much larger scale. I mean, they got their insane InfiniBand network. They've done the performance tuning. They've done the I/O. And this is a platform that, out of the box, it's going to saturate all of that. So that's why they're excited. The pricing is out on these, and it's very, very aggressive in my opinion. Usually the P-series SKUs have some significant discounts as they only work in single socket servers. In the past, it's been as much as half off, but there's much less of a discount here. It's around $1,000, give or take, maybe a little more for some of the more expensive CPUs. The F-series SKUs are incredible values here, I think, giving you high frequency and lots of cache, because you've got 8 compute chiplets as opposed to 4 in some of the other configurations. But I am a bit surprised they didn't go for a single 12 chiplet configuration for the 48 core. I mean, just the one, 12 chiplets, more cache. 12 chiplets is reserved for the highest density parts and with a price tag to match, pretty much universally over 10 grand. And none of these processors are configured for that full 400 watt support out of the box, although you can juice several of them to 400 watts no problem. At the low end, you can give them an extra 10 watts, but usually it's around 20 to 40 watts. I think that's pretty cool. So the pricing is good, but the pricing isn't the whole story. AMD partners benefit from this aggressive pricing because people will adopt CXL and PCIe 5 and DDR5, and those are expensive. I mean, AMD is kind of telegraphing their business move here too, I think, because those features, they're going to drive up the cost of the platform. All those 5s. AMD's telegraphing their business moves here though, I think, because they know that those costs are going to drive up the cost of the platform. And the cost of the CPU in the cost of this newer, more expensive platform, well, the CPU is just a small part of that. AMD is willing to keep the margins reasonable so that you can build a more expensive platform with them with more features versus alternatives that perhaps are more restrictive and that sort of thing. So if you're going to partner up with somebody to build something around this and one of your partners is giving you more flexibility and one of you is giving less, who are you going to partner with? I'm talking about flexibility on the platform. It's PCIe lanes, it's CXL lanes, it's SATA lanes. We know that the 64 CXL interface lanes plus the socket-to-socket lanes that, can be reconfigured. You don't have to have as many, 160 lanes per chassis, remember. And we know the extra PCIe lanes that, are slower for system integrators to use. That lets system integrators differentiate. They can carve out a little niche for themselves. And that's what a partnership really looks like. AMD is giving their partners flexibility to use their CPU product however their customers will most benefit. That flexibility, I think, big picture, taken as a whole, is why I say that this launch is so important for AMD. AMD has buy-in from their partners, and they're giving their partners flexibility, and they're not trying to take all of the profit and the margin from this, I think, with the CPU pricing. So if AMD's bet here, and this is a big bet, is going to pay off, they're in the best position to execute on this if the industry's moving in this direction. Now, I was not able to include any Sapphire Rapids comparisons in this launch because Intel still has a lot of restrictions on the type of benchmarks that can be done with Sapphire Rapids. So I'm going to have to cover that in a future video, maybe when the benchmarking requirements are a little less restricted and or Sapphire Rapids Silicon is a little bit more finalized. And that's really all I can say about that. So congratulations are in order to the whole AMD team. This has been an absolutely phenomenal launch, and I can't wait to do more projects with this platform. It is beyond exciting, and it is really exciting to see so many AMD partners, Microsoft, Oracle, just the huge cloud providers, large and small, Tiger Graph, all the people that I met are super, super, super excited for Genoa. And that excitement's a little bit infectious, but also having a computer this fast, for some reason, makes me really excited. I'm Wendell, this is Level 1. This has been as quick a rundown as I know how to do on Genoa. But if you have questions or you want to see more content or comparisons or benchmarks or you have an open source project and you need help setting something up, contact me. I will be glad to work with you. All right, I'm signing out. You can find me in the Level 1 forums.